For Chapter 3, let's introduce vectors, which is just our way of saying arrows. And what they're going to do is they're going to represent certain quantities. You've already been introduced to some of those quantities, such as displacement, velocity, and acceleration. But so far, we had only done one-dimensional, kind of backwards and forwards displacement, or left and right velocity. And so what we had been doing is just kind of using a plus and a minus to indicate direction. But if we were going to get more complicated with that, we could use arrows to do that. So if we had this motion diagram where an object would have started off here at x equals 0 at time of 0, and then it would have moved to the right to this position x of 2, and then moved left to a position of -1. Before we had said that the displacement is final position minus the initial position. And then we'd get a displacement of -1 meter, and that negative had meant left. All right, and here's now a different way to do that. We can represent it with an arrow from the initial to the final, and just label it delta x. And we have a little bit of notation to remind us when this delta x is actually representing an arrow. You put almost like a little half arrow over it, pointing to the right. So there's our first example of a vector. One important property of vectors is that they have a magnitude, which is a length or a size, and they have a direction. So quantities like displacement and velocity and acceleration, they're all supposed to have an amount, a magnitude, and a direction. So in this case, our displacement, which is a vector quantity, meaning it has a direction, is equal to 1 meter left. So this is going to be the magnitude, which is really just the length of the arrow. And the length of an arrow has to be a positive number, and then this is our direction. So now let's do adding vectors. And usually when we do that, we could say we get the total, or the sum, or the net. So if we had an object, and let's say maybe that there are 3 things pushing on it. Maybe somebody's pushing on it rightward, somebody's pushing on it from here, and maybe somebody's also pushing on it in this direction. And how about we call this maybe push 1? How about we call this push 2? And call this push 3. To find the total, what we're going to do is take the individual arrows and line them up tip to tail to find our answer arrow, to find our net. And a vector is defined as its length, its magnitude, and its direction that it points. It doesn't actually care where it starts. So it's perfectly fine to kind of copy and paste it, pick it up and redraw it somewhere else. as long as you keep the length the same and the direction the same. So P1. And then let's add that to P2. So we're going to take this and redraw it over here, trying to keep the direction and length the same, and P3. Then our answer, our net, will start at the very, very beginning, and it will be an arrow to where we ended up. And it's very important to indicate which direction. It goes from the very, very beginning to the very, very end. And then let's label that as push net, basically meaning the total amount of push. What about subtracting vectors? And that might be called the difference or change in. Usually if we're going to subtract vectors, that might be a final velocity minus an initial velocity. So let me sketch that out. Maybe something had an initial velocity to the right, and it had a final velocity to the left. What is the difference between those? How much change did it have between the initial and the final? So what we could do is say find the change in the velocity. It'll be the final velocity minus the initial velocity. And we're looking at them as vectors now, so I'm drawing those little arrows over the letters. And there's two ways that we can do that. And you just pick one way that works for you. So above, what we had done was what we call the head to tail method. Let me write that in real quick. So we could do that again. Or we could choose to do it by the tail to tail method. So for this one, let's do the head to tail. But what we're going to do is think of it as adding vectors, because the head to tail is the way we add. So what we could do is do final plus a negative initial velocity. So you can see we're going to take an arrow and add it to another arrow, but this is going to be the negative of it. And a negative vector just means a mere flip the direction of it. So what I'm going to do is pick a starting point, copy and paste VF down over here, and then head to tail. So I'm going to start here now to draw the next arrow, but I'm not going to draw VI to the right. I'm going to draw negative VI. I'm going to add on negative VI, which is actually going to be to the left. We take this and we just flip it. So negative VI was here. Right. So then our answer arrow for the head to tail method is just like before, from the very, very beginning to the very, very end is what we were looking for. That's our answer. And in this case, that was the change in the velocity. Now, if you don't like having to imagine the negative of a vector and flipping it, you can use this other method. But that means you have to remember two different ways of doing it. So pick a starting spot, doesn't matter where, and you're going to draw both arrows starting here, kind of lining them up tail and tail here. So the tail of this arrow is going to get redrawn here. And we're going to take this arrow and kind of copy and paste it where the tail of the arrow also lines up there. When we lined them up this way, we had a very beginning point, and then we kind of daisy chained them, and we ended up with a very final point. But that's not the same here. So in order to find your answer arrow here, you have to start the arrow at the beginning of the thing that you were subtracting. So you start the arrow at the end of the initial, and then your answer arrow will stretch to the end point of this. Right, I find it a little bit tricky sometimes to remember which way this arrow is supposed to stretch. So I usually choose to use this method. That way I only have to remember the head to tail method, and my answer goes from the very, very beginning to the very, very end. Some people would choose to do it this way. You just have to make sure that your answer arrow goes in the right direction, from the end of VI to the end of VF. I should add in here a little note. A negative vector, which is what we were dealing with right here, just has the opposite direction. And I'm not sure how much you'll need it, but let's just be thorough and cover the whole section here. Vector multiplication. What if we had an arrow called A? And then what if we multiply that vector by, say, 3? So 3 times A. What would that look like? Isn't that basically just adding A to itself 3 times? So then we could say 1A, add it to another A, and add it to another A, head to tail. So then 3A is really just A, but 3 times longer. What would half A look like? It's really just A, but with 1/2 the length. So instead of having A reach the whole distance, we'll just draw it half the length, and we could label that 1/2 A. And then let's just do one more example. How about if we had negative 3A? So what we could do is we could say take a starting point, and not draw A this time, but draw negative A. And remember, negative just flips the direction. But we had 3 of them. So the negative 3A would be 3 times the original length in the opposite direction.